Hello and welcome to my channel. In today's video we will learn how to get the transfer function of a DC servo motor which is armature controlled. So I will go into these details, but before that, DC servo motors are a very important component in control systems applications. So there is a difference between DC motors and a DC servo motor. DC motors are very cheap while DC servo motors are very expensive, because DC servo motors are kind of a very small closed loop control system. So why we use DC servo motors? We use DC servo motors in applications where we want to get a very precise position. We want to rotate the motor up to a very precise angular position. Then we use DC servo motors. And in order to do that, we have to put a sensor there, which is normally a shaft encoder. And then we use that sensor information as a feedback and try to minimize the error between the current position and the desired position. So this is a very sophisticated closed loop feedback control system. So you can do many things in DC motors. You can use them for a various change in speed applications, change in torque application. You can put a gearbox and you can change the torque as well. And you can also change the direction of rotation by changing the polarity. But for position control, when there is a precise position control required, for example, there is a robotic hand and you want to rotate the hand or the actuator, any robotic actuator, to a very precise position, or for example, you are machining the material and you want to feed the metal to a milling machine, then you want that metal to be a very precise position where you want to make the cut. So in these type of very precise application, we use DC servo motor. Today, when we will derive the transfer function of this DC servo motor, we will get this transfer function in the form of few constants. So there will be few constants, motor constants, and we can find those constants by using some methods, but that we will discuss in the next video, because I don't want this video very long so that you can easily digest the contents in this video. So therefore in this video we will only derive the transfer function of this DC servo motor so that you can know the procedure, and in the next video we will look into the constants, how to find those constant values which will appear in this transfer function. Now coming to this DC servo motor, this is the circuit diagram of the DC servo motor. So we have a fixed field. You can get this field by permanent magnet or by electromagnet, and then armature, the rotating component of the motor. We apply a voltage EA, and then T means it's in time domain, and then the armature current flows. And when we say armature controlled, it means that we are changing the current in the armature. So if it is field control, then we are changing the current in field. But if it's armature controlled, we are changing the current in the armature. And now, what is the purpose of this motor? What motor does? Motor provides the torque. And based on that torque, you can rotate the load, and then you can position the load as well. The torque generated by the motor is T sub M, and position of the motor at any time is denoted by theta sub M. So remember that we are talking about the rotational position. So rotational position is the angle. Just like a linear position or translational position is denoted by x, the distance. But when we are talking about motors, we have to denote the position theta. So when I say theta, it means position. When I say omega, it means velocity. So this is the position, and these are the internal resistance and the inductance. Normally this component is very small. Now when we say transfer function, so transfer function is basically the ratio of the output to the input of the component in S domain. You know that, as I have mentioned already in my previous video when we derived the transfer function of spring mass damper system, that you can take any value. You can take any value as an output and any value as an input and find the relationship between those two values in S domain. So therefore you want to know how to go from time domain to S domain. So there are only 2 or 3 formulas which we will be using in this derivation, and I will explain to you before we start. But this is what we have to do. We have to move from time domain to S domain. So when you know beforehand what we have to do before I start doing something, So then it will be easier for you that you know that what are the critical steps in the derivation of a transfer function. And there are only four. There are only four steps in deriving this transfer function, and I will show you how easy it is to find the transfer function of a DC servo motor. Now, first we have to decide what two parameters we want the transfer function between. So what output parameter is very important for us, and what is the input parameter which is important for us. So as you can see here, the most important parameter for which we are using this DC servo motor is the position. So therefore theta m is very important for us. So therefore we will take theta m as the output variable, and the input, which is very important, is the applied voltage. Applied voltage to this DC servo motor, that is our input. So our transfer function would be G of S in S domain, and our output is the position, and our input would be the applied voltage. So when we go in S domain, we write capital. So our transfer function Gs would be equal to theta ms divided by EAS. So Gs would be equal to the output divided by the applied voltage in S domain. So this is our transfer function. So this is what we have to find. And now how to proceed? You should understand four critical steps, as I mentioned earlier. So what is the first one? The first one is that when this rotor is rotating, it cuts the field, it interacts with this fixed field at a right angle, and due to that it generates a voltage across its terminal. So this voltage, this is called VB. So this is back EMF. So this is the first thing you should understand. So this VBT is proportional to omega, the speed of the motor. So this is also in time domain. So now when deriving this transfer function, you will be using three formulas for Laplace transform. As you know that our transfer function is a ratio in S domain. So we have to move from T domain to S domain. So there will be only three formulas which I am going to write here. So the first formula is that if ft, there is a function of time, and you want to convert this to S domain, so it is simply the function of S. If the first derivative of any function of time and you convert it to S domain, then there will be S and then f of S, and plus some initial condition which we will ignore. If it's a second derivative of time, any function, and we convert into S domain, so we get S square Fs plus two initial conditions which we are ignoring again. So these are the three formulas, very simple, which we will be using here. So now this back voltage, back EMF voltage, which is generated across the terminal of the rotor, is proportional to Wt. So what is Wt? It's the speed of the motor. So when we are interested in position, instead of omega mt, we can write d theta mt by dt. So d by dt of theta mt. So omega is the derivative of position, very simple. So now if you look here, this is the derivative, the first derivative, so we will use this formula. This is simple function, we will use this formula. So now we are going from time to S domain, going to S domain by applying the Laplace transform. So what we get, VBT becomes VBS equals KB d by dt. Using this formula, this is just f dash of theta m. So theta m of S and one S besides this. So this is the first formula. So there will be four critical steps, as I mentioned. So this is the first one. So you can say it's equation 1. So my board is small, so I have to delete this and then I will rewrite it from my notes. But this is the first step. Now, what is the second step? What is the second important thing you have to apply here? So the second important thing is Kirchhoff's voltage in this loop. So this we have to apply. So by applying that, this is the applied voltage. So EAT will be equal to voltage across this, which is the current in the armature, A for armature, in time domain, RA plus LA DI by dt. So this is also A, and then plus this VBT, VB of t. So this is the equation of voltage by using the Kirchhoff's law. Now from this, as we can see that this is a function of time, function of time, function of time, function of time. So we can easily move from time domain to S domain using these formulas, and our second step will be complete. So let's do it. Going from time to S domain, EAT, now we write capital EA and then S, this formula. IA, so this becomes IAS now, into RA plus LA, and what is this? This is the first derivative, so we have to put S here, then IAS, and then what is this VB? VBT is again first formula. So now we have EAS, and remember this is part of our transfer function. This is the input of the transfer function. So this is a good equation. So this is our step 2. If you want, you can take common IAS common from these two terms, so it will be easier for us. So if I take IA common, then I have RA plus S times L sub A plus VBS. Instead of VBS, I can put this value, constant of the motor S and theta MS, and this is also very important because this is our output. This is one of the parameters in our transfer function. So we have to find just the ratio between this and this. Now, in this equation, only we want something theta ms common from these two terms, so that we can take the ratio of these two to get the transfer function. But we don't have any theta ms here. So what we can do, there is an armature current, and now we are going to step number 3. So this was the step number 2. So there are only two more steps which you want to remember when deriving the transfer function. And what is the third step? The third step is your knowledge of the fact that the torque of the motor, Tm, depends on the armature current. That's it. This is the third important knowledge you should have, that the torque of the motor depends on the current of the armature. So if you increase the armature current, torque will increase. So torque is proportional to the armature current. So this is the third important step. And there is one more thing which is also about torque, the fourth one. Here we are saying that torque is proportional to current, and in the fourth and final step, we will be writing the torque equation instead in terms of inertia and the friction, which is the damping here. So last two steps relate to the torque of the motor. So first step, because I have to delete this, so therefore I am reinforcing this thing, that there are only 4 steps. The first step is the back voltage. The second step is Kirchhoff's law on this circuit. The third step is knowing that the torque is proportional to the armature current. And the fourth step is knowing that this torque has 2 components. One is the inertia, this has to overcome the inertia, and the second thing, it has to overcome the friction, because this is the purpose of the torque. Torque has to overcome the inertia, the load which we have to move, and the motor's own inertia, both factors. And the torque also has to overcome the friction, all types of friction. So we will see how we drive the fourth step, but first the third step. So the torque of the motor is proportional to the armature current. So we can say that torque is proportional to the armature current I. So again, I have to remove this, so I will put a constant here, which is now torque constant, Kt, armature current at time t. So again we have to go from t to s domain, function of time. So simply we get Tms constant, and this becomes Ia of s. So this is our formula for the torque. So now we can put this formula in the equation which we got in the second step. So this was our equation which we derived at step number 2. Ra plus SLA into the armature current in S domain plus KB S theta ms. And now we got the value of armature current in S domain from here. So if we put that value on this place, then this equation will change. So thus just put this, the value of IAS, which is equal to the torque divided by Kt. So I have to put this value here. So what I get equals Ra plus SL sub A Tm over Kt. So I can just put it here at the moment, plus Kb S theta ms. Now again, same approach. We want to get a ratio between theta ms and IAS. This is constant, this is constant, this is constant. The only thing which we don't want here is this theta ms, torque of the motor. We don't want this. We want something which contains theta ms, so that we can take theta ms common and then simply take the ratio of these two and we get the transfer function. Very simple. So this was the third step. This is the position after the third step. You can say this is the third step, but when you put the values, this is the position after the third step. So the fourth and the most important step is, you can visualize here that we want the value of TMS, the torque. We want the value of torque in terms of theta. if we could get the value of torque in terms of theta and put it here, this torque will be gone, theta will come here, and we can then take common theta ms and then take the ratio of theta ms with this and get our transfer function. Very simple. So now the last question is how to get this TMS in terms of theta ms, the position of the motor. And in order to get this, we have to understand the loading of the motor. So it's a little bit of introduction. Half of this part we will understand in the next video when we will find the constants, the torque constant and the KB, the back EMF constant. But for this video, I will explain a little bit about how we load the motor and what happens. Let's say this is the shaft of the motor and we apply a torque and it will go to a position. Now this torque has two jobs. One is to overcome the inertia, and that inertia is Jm multiplied by the rate of change of omega. So this is the first part which torque has to do, to overcome the inertia. This is just like, you can, it's not an exact comparison, but you can say that just like mass in the linear motion and acceleration in the linear motion. So this is first part. So this torque has to overcome, number one, this thing, and number two, there should be an associated damping with this, and that is called viscous damping or the friction. Because whenever there is a velocity, that is called the friction to that velocity is called damping or the viscous damping. And as in the linear motion, we have the formula damping coefficient into x dot. So this is the formula which we already used when we were driving the mass spring damper system. We use this formula, a damping coefficient into the velocity, linear velocity. So similarly in rotational velocity, we also have this friction present there, which is called viscous damping, and the similar type of formula, and that is, instead of C, we are using here D, damping motor, and instead of x dot, we use of course omega in our case. So this torque has to overcome these two things, the inertia and the friction. So this is inertia and this is friction. So actually this motor must be attached with a load, some load. So the rear diagram, which we will discuss in the next video, this motor has some gear, you can see, and then there is a load attached. So this is load, and then we have a damping here. So basically it is something like this. This load is contributing to the total inertia which is overcome by this torque. So this load will also be contributing, and the ultimate contribution comes to the armature winding. So this load effect is also included in DM, and this load effect is also included in this JM. So therefore, but this we will discuss in next video. But here you can say that this torque has to overcome two things, the inertia and the friction. The formula for inertia is this, and the formula for the friction is just like we had in linear motion, the damping coefficient multiplied by velocity the damping coefficient or the viscous damping coefficient multiplied by the angular velocity. So now this is the formula of Tm, and if you look here, you can replace this with theta, you can replace this with theta. So this is what we have to do next. So torque in time domain equals Jm, no, d and omega by dt, d by dt, and if you replace omega with d by dt of theta m, so now we have d square theta divided by dt square plus dm, the damping, into omega, which is d theta m by dt. This is omega. So we get torque equals Jm d square theta m dt square plus dm d theta by dt. So now we have torque in terms of theta. So as you can say, now we got the torque in terms of theta. This is what we were looking for, the value of torque in terms of theta. So the only thing left is we have to go to S domain using again the same formulas. This is the square formula, this one. So when we go to S domain, we get torque equals Jm, and this is S square theta ms plus dm s into theta ms. So this is the final step. This is the final step. Now we have Tm, the value of torque in terms of theta ms. So if I put this into here and then take the ratio of theta ms divided by this, I will get the transfer function. So very simple. So this is how you get the transfer function of a DC servo motor. The rest is only you have to put this value here. So I will put this value in, and then you can simplify, but what you have to do is EAS equals RA plus SLA multiplied by, instead of this, we can write this whole equation. Jm S square theta ms plus dm s theta ms divided by kt. I am writing here because I have to just show you one thing, plus this term kbs theta ms. Now once you have written this, then as I mentioned earlier that the inductance component of a DC motor is very small as compared to the resistance component. So therefore we ignore this LA, we take this to 0. So this is the only thing you have to put here, LA equals 0. So this is you have to put. So if you do that, what will happen next? EAS. Now this term will become 0. So you have to only multiply RA divided by KT with this term. So now you have all three terms here. So first I multiply only this RA with these two terms. So I get Jm S square theta ms plus dm s theta ms plus kb s theta ms. This should be kb, because when I take this thing common, kb will be inside. So kb plus this factor multiplied by jm, and 1s left here, and here only dm is there. So now we have to take the ratio of theta ms with the applied voltage Es, and when we do that, so I have written the last step here again. So that now we can just take this first below this, so EAS divided by theta ms equals S, and we put this S terms first. So S into Jm Ra divided by K sub T plus, you can take this Kb next, and then you can take this Ra K sub T Pm. So now what we want to do, we want to make this first let's take the reciprocal of this, so that we can take this into the denominator, because our transfer function is theta m divided by Es. So just take the reciprocal of both sides, so we get theta ms equals 1 divided by S multiplied by S into JMRA K sub T, so plus KB. So now we want to get rid of this coefficient of S here. So what we can do is we can multiply the reciprocal of this, so it will be multiplied by all these three terms. So we multiply this with KT, K sub T divided by Jm R sub A. So we have to do this in the numerator as well. So multiply in the numerator. So K sub T divided by Jm R sub A. So because we want this coefficient of S to be 1. So now we are almost there. So on the numerator we get this term K sub T Jm R sub A, and on the denominator when you multiply this with this, you get only S. So S here, then S plus KB multiplied by this is KB KT divided by JMRA. JMRA, and when you multiply this with this term, this RA will be cancelled out, KT will also be cancelled out, so we will be left with DM divided by Jm, and we can take common again 1 divided by Jm, so we can take from these two terms. So this I will do next. So this is our transfer function on the left hand side. It is the ratio of the position of the motor divided by the applied voltage. So this is our transfer function. I just want one more step to simplify this, so that we can take this 1 divided by j common. Otherwise you can keep it here, it's perfectly fine. So our transfer function equals, in the numerator we have k sub t slash jm r sub a s plus 1 divided by jm is common from this, and inside we have kb k sub t divided by ra plus dm. So this is normally we write it like this. If you look in any book, you will see something like this. So now this transfer function is in the form of some constants, and this we will find in our next video. So I hope that now you understand that there are only 4 critical steps if you want to find the transfer function of a DC servo motor. I hope you find this video useful. If so, please like this and subscribe to my channel if you are interested in control systems video. And thanks for watching.